Hello, this is Dr. Webb, and in this video we're going to be introducing one of the most important and useful derivative rules, and it's called the chain rule. So let's go back over some derivative rules we've seen so far. So first, if we're taking the derivative of a constant, so this c here is a constant times a function, well, we can just pull that constant out and just get the constant times the derivative. If we want to take a derivative of a sum, it's just going to be the sum of the derivatives. And then in the last video we talked a bit about the product rule, saw the product rule in action, and so that means that if we're taking the derivative of two functions times each other, it's the derivative of the first, so f prime times the second times g, plus f of x times g prime of x. And one good way to remember the rule for this is that if you calculate f, you take f and g, you calculate f prime and g prime, well then f prime g is that diagonal, and fg prime is the second diagonal, and so you add those two together. And then another rule we saw is that if you're taking the derivative of x to a power, positive or negative, you can just pull that power down. So if you're taking the derivative of x to the n, you can pull the n down and then subtract 1 from the new power. So you get n times x to the n minus 1. So like if we wanted to do derivative of x to the 75, that would be we take the 75 down, take x, and then subtract 1 from that, and so that would be x to the 74. Okay, so what we're going to talk about today is how do we take derivatives of compositions of functions. So here we're talking about where we have one function plugged into another one. How are we going to take derivatives of that? So here we're thinking about taking derivatives of things like this, where this g of x, we're going to think about this as being our outside function, or our inside function is g of x, and then f of x, this is our outside function. What happens when we plug one function inside the other and then take the derivative? Okay, so let's go through this and let's start looking at this by an example. So we're going to take the derivative of 1 over x squared plus 3. Okay, so first of all, how can we think about this as a composition? So if we want to think about this as being f of x with g of x plugged in, what is f and what is g? So what is f, what is g? And it's often the case, it's usually kind of best to think about things inside out. So really, so again, we're looking at what's the inside function, what's the outside function. So what stuff is going on here? Well, we've got this x squared plus 1. This is sort of deep down, this is the innermost thing. So that's going to be our inside function. And then what's happening to x squared plus 3? Well, we're dividing by it. We're taking the reciprocal of it. And so the outside function is going to be 1 over x, because we're taking the reciprocal of x squared plus 3. So we're taking x squared plus 3 and plugging it into 1 over x. Okay. So if we want to take the derivative of this, let's go back to use our limit definition of derivatives. So we're looking at the limit of as delta x goes to 0, and then plugging things in. So this top up here, this term right here is, let's not use x. Let's call that something else. Let's call it h. Minus h of x. Okay, so if I'm plugging in x plus delta x in for x, I get 1 over x plus delta x squared plus 3, and then minus 1 over x squared plus 3. Okay, so we've got fraction inside of a fraction. Don't particularly like that, so we want to clear out our denominators. So what do we need to multiply by? Well, to clear out the first one, clear out this first one, we're going to need to multiply by x plus delta x squared plus 3. And then to clear out the second one, we need to multiply by x squared plus 3. Let's go back. So in the first one, that term is going to cancel off with this one and leave the x squared plus 3 on top. In the second term, x squared plus 3 is going to be canceling off the x squared plus 3 there, and we're going to be left with that on top. And all of this, we got to remember that if we're multiplying this to the top, we got to do the same thing to the bottom. And I'm going to run out of space here, but I'll do my best. So when we multiply that out and through like that, what do we see happen? We end up with something that looks like this. And so you can see this right here is the common denominator that we multiplied by. Okay, so now as we're looking at this, how are we going to be able to cancel things off? Well, probably going to be easier to, we're going to need to expand this guy out right there. So let's do that. And so when we expand him out, the x plus delta x squared turns into x squared plus 2x times delta x plus delta x squared. Now we can look up top and see what can be canceled. Well, we've got an x squared there, and then a minus x squared there, so x squared minus x squared. Those guys are going to cancel each other off. Then we also have this plus 3, and then minus plus 3 over there. So they're going to cancel each other off. And so what we're going to be left with on top is 2x plus delta x squared. So I think we go to the next slide. Yeah, so as we remember, that's going to cancel with that. That cancels with that. And we're left with minus 2x times delta x minus delta x squared on top, and then divided by delta x times our common denominator on the bottom. Well, and so now when we look at this, we see we've got a delta x here, and we've got a delta x squared there. So both terms on top have a delta x. So we can factor that delta x out and cancel it with the delta x on the bottom. So that's going to disappear. What are we left with on top? Minus 2x minus delta x over our common denominator from before. At this point, thinking about this limit, we want to take delta x goes to 0. We couldn't do that when there was a delta x getting multiplied on the bottom, but now we've canceled that delta x out, and so now there's going to be no problems plugging in 0 for delta x. So we can do that. We end up with minus 2x plus 0 on top, divided by x plus 0 squared plus 3 times x squared plus 3. And we can simplify down and get that down to minus 2x on top, and then it's just going to be x squared plus 3 quantity squared on the bottom. Okay, so this is what the limit definition tells us the derivative is. Okay, so we want to use this to think about, what happens when we take the derivatives of compositions of functions. So as we saw before, we can see this as being a composition as being derivative of f of g of x, where f is 1 over x and g is x squared plus 3. Well, so we're taking a derivative, so it might be helpful to know what the derivative of both of these functions are. And so what's the derivative of 1 over x? Well, we've looked at this before. It's going to be minus 1 over x squared. What's the derivative of x squared plus 3? So it's a sum. So it's going to be the sum of the derivatives. So the derivative of x squared, power rule says that's going to be 2x. And then derivative of plus 3, derivative of a constant is just 0. And so these are our f of x, our g of x, our f prime, and our g prime. We found the derivative to be minus 2x over x squared plus 3, quantity squared. Well, let's see where we can connect things together. Right, so we've got x squared plus 3 there. And we've got x squared plus 3 sitting right there. We've got a 2x on top, and that sort of matches 2x right there. And then if we look at kind of the shape of everything going on here, well, I've got a minus on top and then something squared on the bottom. Well, what looks like that? I've got a minus 1 divided by x squared on top. And so really it might be more helpful to think about this as being minus 1 over x squared plus 3 squared times 2x. And so bringing the colors back, that's our yellow, that's our green. So how did everything get fit in? Well, this 2x out here, this is our g prime. Our yellow, this is g of x. And then g of x is getting plugged into our blue. And our blue is f prime of g of x. So if we're thinking about this in terms of f of g, what did we end up with at the end? Well, we have the derivative of f with g of x plugged in. And then at the end, we then are multiplying by g prime of x. And in fact, that is what the chain rule is. So if you want to take the derivative of g of x plugged into f, well, what you get is you get g of x plugged into the derivative of f, and then outside you're multiplying by the derivative of g. Right? So you can kind of think about this as being derivative of the outside. So derivative of the outside with the inside plugged in times the derivative of the inside. Okay, so why does this work in general? So let's look at playing around with this limit in just general functions f and g. Kind of thinking about the same thing that we did before. Right, so we're going to use the limit definition. This, I'm just plugging everything straight in for the limit definition. So this is plugging in x plus delta x in for x into here, and then subtracting off with what we started. So in some sense right here, we can remember that sometimes we think about this g plus delta x minus just g of x. We can think about that talking about the change in g. So if we start off at this point and solve for the g of x plus delta x, so if we move the g of x over to the other side, we can see that if we're thinking about it like this, we can think about g of x plus delta x being equal to g of x plus delta g. Right? And so that's really how we're going to think about this part right here. We're going to think about this as being g of x plus delta g. Right, and so there we've written it in right here. Well, what's the nice way? What's the reason for doing this? Well, now the inside over here, that looks much more familiar to us. That looks a lot closer to what we're used to seeing when we're taking derivatives of something plus the change in that minus f of the something. But the difference here is here we have delta g, and so if we wanted things to match on the bottom, we should have delta g there too, but instead we have delta x. And so in some sense, if we think about the things that we've been doing, we'd be a whole lot happier if we had delta g in both of those. So how can we work that in? Well, we're just going to multiply both the top and bottom by delta g. Okay, and so then when we do this, rearranging, so I'm going to swap the delta g and the delta x there, swap their places. It's just multiplication in the denominator, so that's completely legal to do. And now, what do we end up with here? Well, this looks like now we have the delta g here matching the delta g there. And then over here, we've got change in g divided by change in x. Okay, so I'm just comping out what we have right there. So we got these two things multiplied to each other. And so in a limit, if we have a multiplication inside a limit, we can break it up into two limits. Now if we look in this second limit right here, we're taking the limit as delta x goes to 0 of the change in g over the change in x. Well, hopefully that looks familiar to you. That is the g prime of x that we saw before. And then over here, we're taking g of x plus delta g minus f of g of x divided by delta g. So now these are matching. One difference is now we have delta x goes to 0 here. But the one thing to note is that as delta x goes to 0, well, that means we're not changing x at all. And so if we're not changing x, that means we're also not changing g. So as delta x goes to 0, delta g is going to 0 as well. And so we really can think about this as being the derivative with g plugged in instead of just x. And so this whole bit right here turns into the derivative of f with g plugged in. So that's where we're getting our f prime of g times g prime of x. So here is our chain rule. We're going to be using this lots and 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 lots in the coming weeks. So let's do a quick example. So here we're taking the derivative of x squared plus 3x plus 1 quantity to the 102nd power. Now if you wanted to do this, you could just multiply x squared plus 3x plus 1 out 102 times. You are welcome to do that. That idea will work perfectly fine. I instead am going to think about this using the chain rule, make this a bit faster. So again, if I'm thinking about what my inside function is, let's call that g of x again. So this is my inside. Well, my inside part is the x squared plus 3x plus 1. Well, then what is happening to that g of x? That's my outside part. We'll call that f of x. So this is outside. So what's happening to my g of x? It's getting raised to the 102nd power. So my f of x is, I'm taking something x and raising it to the 102nd power. And so now you can kind of see now that this is talking about f of g of x. Okay, so if we want to take the derivative of this, derivative of x to the 102, that's just the power rule. 102 comes down, x to 1 power less, so that's x to the 101. G prime, we've got x squared plus 3x plus 1, taking the derivative of that, so just do it one by one. Derivative of x squared is 2x. Derivative of 3x is 3. Derivative of 1 is just 0. So really it's 2x plus 3. All in. Let's finish this off. Chain rule is f prime g of x times g prime of x. So f prime g of x times g prime of x. Well, f prime is 102 to the 101. My g is x squared plus 3x plus 1. And then at the end, I'm going to multiply by the derivative of the inside, which is 2x plus 3. So overall, derivative here is 102 to x squared plus 3x plus 1 to the 101 times 2x plus, and so then when we plug that, so just as we said, derivative of x squared plus 3x plus 1 to the 102. From the outside, raising things to the 102. So the power comes down. We got 102 right there. New power is 101. And then at the end, we have to multiply by the derivative of the inside. Okay, so here's some practice problems to work on. So first, this is very similar to the last one. Taking the derivative of 2x minus 1 to the third power. I put the next two together. And then, okay, so next two, you can see these are actually pretty similar to each other. Just think carefully how you think for each of these, what is the inside or inside function, and what is the outside? And picking these well is going to make this a pretty straightforward task. So I will see you soon. Goodbye.